Hello, welcome back. So today we're going to go through the derivation of the elemental qualities for the 2D constant strain triangle. This is one of the most popular elements out there when you first learn the finite element method, and its derivations are actually very similar to what we did in 1D, but now with the matrices are larger. For example, the material matrix, instead of being like E was a scalar, Young's modulus, it's now like a matrix. And so there are some important differences, but it's very similar. It also helps reiterate what we learned in the 1D. So let's get started. You remember here we have our total potential energy of the system, pi, and we have our strain energy term, our force term, our tractions, and our point loads. So we want to start by taking a look at this this value here, this strain energy term, okay? And we are going to write that 1/2. We're going to have the integral over the volume of sigma transpose epsilon dV. So that's actually what it would be in the full three-dimensional case. Okay, and we're going to simplify it here for our 2D considerations. We can do some things here. We know that what is sigma? Sigma is equal to d times, it doesn't look like a p, but this is actually supposed to be d times epsilon. If you remember, the d is a symmetric material matrix. We talked about it in the very beginning of class, and we're going to go over it again here, but that's what that is. So we have d epsilon. Remember, epsilon is in void notation, so it's a vector, the way we represent it. And so we substitute this in, we're going to have 1/2 the integral over the volume d epsilon transpose times epsilon, okay, dV. Now, if you remember, what do we do here with that transpose? We flip and we distribute, right? So this is going to be equal to 1/2 integral over the volume epsilon transpose d transpose epsilon dV. Okay, d is symmetric, so actually d transpose is equal to d, and the volume term, this thing here, is going to be equal to T times dA. So a thickness of what we're considering times the area. So we're really moving this to an area integral by considering the thickness and getting rid of that dV. So then we're going to have finally 1/2 the integral over the volume, the epsilon transpose d epsilon T dA. Okay, so we can then substitute that back into our total potential energy, and we can employ the idea of discretization. So we can put a sum, apply this to each element, and put the sum in front. So let's draw a line here. So pi is going to be equal to the sum over all elements, the integral over the element, epsilon transpose d epsilon T dA. And let's do this with the other elements also. So we have the sum over elements, the integral over the elements, u transpose f T dA minus the integral over the length for our traction. So we have to go over what that length means, times the tractions L dL, and minus the sum of u I pi. And this one's a transpose. So that's our point load. Okay. Ran out of space there at the end, but hopefully you can see that. So this is the element strain energy. Let's take a further look at that to get the stiffness. So we have UE is equal to 1/2 the integral over the element epsilon transpose d epsilon T dA. Epsilon is equal to what in isoperimetric form? We know that's equal to B times Q, right? So then we can substitute that in. UE is equal to 1/2 integral over the element BQ transpose D BQ T dA. All right. if you remember D and B, so let me write up here, D is equal to E over 1 minus nu squared. We're going to have 1 nu 0 nu 1 0 0 0 1 minus nu over 2. Okay, so it's kind of sloppy. We have that as our D matrix. Remember, that was a 6 by 6 symmetric tensor, but now for plane stress it simplifies to 3. If you remember that discussion on plane stress and plane strain in near the beginning of the course. So we have our D matrix here. Okay, B is constant. This is constant over element. We talked about that last time when we filled in the values of B. So then we can move some of this stuff outside the integral. So as a result, we're going to have 1/2 Q transpose B transpose. Notice I'm also going to distribute that transpose and flip them. Okay, that's why I have the B transpose in front. And then we're going to have D, B, T, and then the integral of the quantity times quantity of the integral over E dA. Okay, everything else is outside of that integral sign. So this thing here, what is this? It's just A sub E, it's just the element area. It's pretty neat. Okay, so then we can write 1/2 Q transpose KE Q with KE, the elemental stiffness matrix for constant strain triangle, is equal to B transpose D B T sub E A sub E. Okay, so that's awesome. What do we got? We have a B is a 6 by 3, right? 6 by 3. D is going to be a 3 by 3. We have B is a 3 by 6. B transpose is a 6 by 3. Then we're going to have a 3 by 6, and that leaves us with a 6 by 6. Okay, so all that gives us a 6 by 6 element stiffness. Okay, so we're going to pause the video here. In the next one, we're going to move on to the force term.